Hi, this is Dr. Bay, and here's Bugsy. And today we're going to talk about a qualitative approach to understanding acids and bases when you do not have the pKa values handy. We'll delve into this by looking at molecular structure, acidity, and Lewis acids and bases. Stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
From what we learned last time, we can use pKa values to predict the position of equilibrium by identifying the pKa values of the acids on each side of the equilibrium. Recall that equilibrium will favor formation of the weaker acid, meaning the one with the higher pKa value. So in this example, it will favor the right side. But what if you didn't know the pKa values? What do? Well, that's when we turn to using the molecular structure to determine the position of equilibrium. To do this, we're going to look at the conjugate base of each acid. Remember that the strength of acids is opposite to that of bases. By determining the more stable, weaker conjugate base, we can identify the stronger acid. In this case, the base on the right side is much weaker, meaning its corresponding carboxylic acid is strong. Equilibrium will lie on the side of the more stable base, and this approach does not allow us to predict exact pKa values, but it does allow us to compare the relative acidities of two compounds quickly without the need for a chart of pKa values. So how do we know that the hydroxide ion is less stable than the carboxylate ion? Well, that's when we can turn to the four different factors that affect anion stability, ARIO. Anions are more stable when the negative charge is 1 on a more electronegative atom or a larger atom, 2 delocalized through resonance, 3 decreased by inductive effect, and 4 in an orbital with more s character. And I'll break down what each of these mean for the remainder of this video. When comparing two atoms bearing the negative charge that are in the same row on the periodic table, electronegativity is important because it tells us how willing an atom wants to attract electrons. The greater the electronegativity of the atom, the more stable the anion is, and therefore the stronger the acid. Let's look at an example by ranking the following acids from strongest to weakest. First, we have to deprotonate each hydrogen in red to form their corresponding conjugate bases. Now we can compare each of the atoms with the negative charges. If we highlight each of these atoms and look at their positions on the periodic table, we see that carbon, nitrogen, and oxygen are all in the same row in the periodic table. Based on the electronegativity trend, carbon is least electronegative while oxygen is most electronegative of these three atoms. That means that the conjugate base with oxygen is the most stable or weakest conjugate base, which means its corresponding acid is strongest. On the other hand, the conjugate base with carbon is the least stable anion or strongest conjugate base, which means its corresponding acid is the weakest. And the conjugate base with nitrogen is in the middle. Now, what do you do if the atoms you're comparing aren't in the same row? Well, rather than looking at electronegativity, you're going to look at atomic size. Atomic size is a measure of negative charge stability. The larger the atom, the more space the negative charge can spread over across. So the larger the atom with the charges, the more stable the anion is, and therefore the stronger the acid. Let's take a look at this example. Rank the acids from strongest to weakest. So first, we're going to deprotonate each of these acids to form their conjugate bases. Now we can compare each of the atoms with the negative charges. If we highlight each of these atoms and look at their positions on the periodic table, we see that both oxygen and sulfur are in the same column, which means we have to compare them by their atomic size. Sulfur has a larger atomic radius than oxygen based off of the trend that going down a column increases its atomic radius. That means the conjugate base with sulfur is a more stable anion, meaning its corresponding acid is stronger. Since the conjugate base with oxygen is a less stable anion, its corresponding acid is weaker. The second factor you could use to determine anion stability is resonance. Resonance delocalization of the charge in the conjugate base makes the anion more stable, meaning its corresponding acid is stronger. In this example, let's compare the two protons in red and blue and determine which proton is more acidic. To do this, we have to look at each conjugate base one at a time, so let's only deprotonate the red hydrogen for now. Notice that the charge is localized. There is no resonance stabilization because both adjacent carbon atoms are sp3 hybridized. Remember that for resonance to occur, you need at least 3 sp2 hybridized atoms in a row. Now let's look at the second conjugate base, where we only deprotonate the blue hydrogen atom. Notice that the nitrogen, carbon, and oxygen atoms all have unhybridized p orbitals in which pi electrons can flow into. One lone pair from the nitrogen atom can push to form a CN double bond, and the CO double bond can break to form a new lone pair of electrons on the O to form a second resonance contributor. Since the negative charge is delocalized over the two equivalent resonance structures, this makes this particular conjugate base much more stable, or a weaker conjugate base. Therefore, its corresponding acid is stronger. This means that the blue hydrogen is more acidic because the negative charge on its conjugate base is delocalized by resonance. The third factor that we can use to determine anion stability is inductive effect. The polarization of electron density of a covalent bond is due to the electronegativity of an adjacent covalent bond. Inductive effect is affected by electronegativity, number of electronegative atoms, and distance. Note that this is different than atom electronegativity of the atom bearing the negative charge. In this example, all the hydrogen atoms that are being deprotonated are attached to the oxygen atoms. So the other trends that we just learned previously could not be applied in this example. So the only option is to look at anion stability through inductive effect. Note that with each additional chlorine atom, the proton becomes more acidic. And the fourth and final factor that we can use to determine anion stability is by looking at orbital hybridization. For anions differing only in the hybridization of the charged atom, the greater the percent of S character in the atom, the more stable the anion is. So sp hybridized atoms would be more stable than sp3 hybridized atoms. In this example, let's compare the acids from strongest to weakest. First, let's deprotonate the hydrogen atoms to form their corresponding conjugate bases. Now, just by comparing the carbon atoms that bear each negative charge, we can determine their hybridizations. The alkane on the left has sp3 hybridization, meaning it has 25% S character. The alkene in the middle is sp2 hybridized, meaning it has 33% S character. And the alkyne on the right is sp hybridized, meaning it has 50% S character. This means that alkane is the weakest acid since its conjugate base was the least stable, and the alkyne is the strongest acid since it had the most stable anion, and the alkene lies in the middle. So in summary, to compare the acidity of two compounds qualitatively without pKa values, we should look at their conjugate bases. Anion stability can be described using four factors: atom, resonance, induction, and orbitals, or ARIO. For elements in the same row, electronegativity is dominant. For elements in the same column, atom size is dominant. Secondly, resonance delocalization of the charge in the conjugate base makes the anion more stable. Thirdly, inductive effect is affected by electronegativity of adjacent atoms, the number of these adjacent electronegative atoms, and its distance from the atom bearing the charge. And lastly, for anions differing only in hybridization of the charged atom, the greater the percent of S character, the more stable the anion is. In terms of ranking, atomic factors are most important, and then take a look at resonance, then induction, and orbitals as the least important of the four factors.
Organic.